Hello, I am Get Handler and I have come back after leave and like Get Handler and Get Willy. I also started a series on learning physics with seeing the beautiful sights of Indian villages. And firstly, I would like to pray the devotee of Ram Hanuman, Jai Bajrangbali. Please help me, Bajrangbali. I want to go back my own country with a hike of 1000 times in my salary as like Get Willy and Get Handler God. So please, Hanumanji Bajrangbali, please help me so that I can go back to my country and work there and my salary will hike with a 1000 times. Now let's come to the point. Jai Shri Ram, Jai Shri Ram, Om Namah Shivaya. Today in this topics I would like to give some important points regarding oscillatory motion. So let us start oscillatory motion. The first topic in this is periodic and oscillatory motions. The first define periodic motion. Any motion which repeats itself after regular interval of time is called periodic motion. The time interval after the motion is repeated is called time period or period of motion. Some examples of periodic motions are motions of a ball in a bowl, motion of a liquid in a U-tube container, motion of a hand of a clock. The period of motion of hours and of a clock is 12 hours, and of minutes hand of a clock is 1 hour, and of second hand of a clock is 1 minute. Motion of electron around the nucleus. These are the examples of periodic motion because these all motion repeat itself after a fixed period of time. The another point, let's see. A periodic motion can be either rectilinear or closed or open curvilinear. In case of a periodic motion, force is always directed towards a fixed point which may or may not be on the path of motion. Now the definition for oscillatory motion. A periodic motion in which body moves to and fro or back and forth along the same path about a fixed point called mean or equilibrium position is called oscillatory or vibrating motion. These types of motion is constrained periodic motion between two fixed limits called extreme position on either side of mean position. Some examples of oscillatory motion is motion of the pendulum of a wall clock, motion of needle of a shaving machine, motion of the prongs of a tuning fork. You know, this is the area of Maharshi Jayaprasadeshwar Gupta. I also like to pray that Maharshi Shri Jayaprasadeshwar Guptaye Namah. Om Namah Shivaya. Jai Bajrang Bali. Jai Hanuman Ji. Jai Shri Ram. Jai Sita Ram. Please help me. Ram Ji, please help me. Hanuman Ji, Bajrang Bali, please help me. I want to get back to my own country with a hike of 1,000 times in my salary. Please, please, please. Hanuman Ji, please, Bajrang Bali, help me. Next list comes to the point. Every oscillatory motion is a periodic, but every periodic motion need not to be oscillatory. For example, circular motion is a periodic, but it is not oscillatory. Now, we would see some terms related to the periodic motion. The time period, it is defined as the smallest interval of time after which the motion is repeated. It is denoted by the symbol capital T, and its SI unit is second. The orbital period of the planet Mercury is about 88 Earth days, and the Halley's comet appears after every 76 years. Frequency, it is defined as the number of oscillation per unit time, and it is denoted by the symbol nu or sometimes a small f. The relation between frequency and time period is in the form of formula is given like nu equals to 1 by t, that is frequency equals to 1 by time period. The SI unit of frequency is hertz. That is 1 hertz equals to 1 Hz equals to 1 oscillation per second or 1 per second. The bit frequency of heart is 1.25 Hz and its period is 0.8 seconds. The frequency is not necessarily an integer. It may be a fraction. It means Jai Bajrang Bali, please help me. I want to go back to my country. Angular frequency omega. The angular frequency omega is given by 2 pi nu or equals to 2 pi by t. The SI unit of angular frequency is radian per second. Now the next term is displacement. It refers to change in physical quantity under consideration with time. It represents change in physical quantities with time, such as position, angle, pressure, electric and magnetic fields, etc. In case of an oscillating simple pendulum, the angle measured from the vertical as a function of time is displacement variable. The displacement variable is measured as a function of time, and it can have both positive and negative values. Displacement can be represented by a mathematical function of time. That is, in case of periodic motion, the displacement can be given as x equals to function of time, that is ft, equals to a cos omega t, or y equals to ft equals to a sin omega t. Here ft represents function of time and a is called amplitude of the oscillation. Let's now the next topic is periodic function. A function ft is said to be periodic if ft equals to ft plus cap t, where cap t is the time period of the periodic function. Sin omega t, cos omega t, sin omega t plus cos omega t are the periodic function with a period of 2 pi by omega. Any periodic function can be expressed as a superposition of sine and cosine function of different time periods with suitable coefficients. E to the power minus omega t and log omega t are non-periodic functions. Now let's see simple harmonic motion. Some important points related to simple harmonic motion. Simple harmonic motion, SHM. It is also represented as SHM. It is a kind of periodic motion in which a particle moves to and fro or up and down about a mean position under a restoring force, which is always directed towards the mean position and whose magnitude at any instant is directly proportional to the displacement of the particle from the mean position at that instant. In mathematical form, it is written as f proportional to minus x, or f equals to minus kx, where k is known as the force constant. The negative sign shows that restoring force F is always directed toward the mean position. Examples of simple harmonic motions are motion of a bob of a simple pendulum. Motion of a block connected to a spring is also an example of simple harmonic motion. The SI unit of K, that is force constant, is Newton per meter. and its dimensional formula is capital M L to the power capital L to the power 0 t to the power minus 2. Every periodic motion is not simple harmonic motion. Only that periodic motion governed by the force law F equals to minus kx is simple harmonic. Geometrical interpretation of simple harmonic motion. Simple harmonic motion is the projection of a uniform circular motion on a diameter of the reference circle. Yeah, Bajrangbali, please help me. I want to get back to my country. I am remembering my home and my people. Please help me so that I get a job in my home country with a hike of 1,000 times of salary like get Willy and get handler. Now, simple harmonic motions are of two types. Linear simple harmonic motion, when a particle moves to and fro or up and down about a mean position along a straight line, then its motion is called linear simple harmonic motion. Example, motion of a block connected to a spring. The second one is angular simple harmonic motion. When a system oscillates angularly with respect to a fixed axis, then its motion is called angular simple harmonic motion. That is motion of a bob of a simple pendulum. Let's make a comparison between linear SHM and angular SHM. The first comparison, restoring force. A linear SM is restoring force, angular SM is governed by restoring torque. The formula in linear SM is F equals to minus kx. The formula in angular SM is tau equals to minus c theta. Here tau represents torque, c represents restoring torque constant, and theta represents angular displacement. Similarly, in F equals to minus kx, F represents force and k represents restoring force constant, and x is the linear displacement. And restoring force constant is defined as restoring force per unit displacement. Similarly, restoring torque is defined as restoring torque per unit twist or angle. Next point, in linear SHM, acceleration is given by a small a equals to minus k by m into x, and similarly in angular SHM, angular acceleration is given by alpha equals to minus c by I into theta, where I is the moment of inertia of the body. Similarly, in angular linear acceleration, m is the mass of a body. Now the differential equation of linear SMH is d2x by dt square plus omega square x equals to 0, where omega square equals to k by m. Similarly, the differential equation of angular SMH is given by d2 theta by dt square plus omega square theta equals to 0, where omega square equals to c by I. Now let's see displacement in simple harmonic motion. The displacement of a particle in SMH at any instant t from its mean position is given by x equals to a cos omega t plus phi and y equals to a sin omega t plus phi, where here a is capital, where capital A is the amplitude, that is maximum displacement on either side of mean position. The argument omega t plus phi is the phase of the motion and phi is the initial phase or phase constant or phase angle of the motion, and omega is the angular frequency. Now velocity in simple harmonic motion. The velocity of a particle in SM is given by v equals to dx by dt. Dx by dt means differentiation of x with respect to time. V equals to dx by dt equals to minus omega cap a into sine omega t plus phi, with v equals to omega into under root cap a square minus x square. In SHM, that is simple harmonic motion, velocity is maximum at the mean position and minimum at the extreme position. The direction of velocity of particle in SHM is either towards or away from the mean position. The maximum value of velocity is called velocity. Amplitude called amplitude in SHM and is given by Vm equals to a omega. That the maximum value of velocity in SHM is called velocity amplitude and is given by Vm equals to v subscript m, that is Vm equals to a omega cap a into omega. In SHM, the velocity varies simply harmonically with the same frequency as that of the displacement. In simple harmonic motion, the graph between velocity and displacement is an ellipse given by v square by cap a square omega square plus x square by a square equals to 1. If omega equals to 1 radian per second, then the graph will be a circle. That is omega angular frequency is equal to 1 radian per second. Then graph is a circle. Now acceleration in simple harmonic motion. The acceleration of particle in SHM is given by a equals to dv by dt equals to d2x by dt square equals to minus omega square into capital A into cos omega t plus phi. That is A equals to minus omega square x. In SHM, acceleration is maximum at the extreme position and minimum at the mean position. In SHM, acceleration is proportional to the displacement and is always directed toward the mean position. The maximum value of acceleration in SHM is called acceleration amplitude and is given by am equals to omega square into capital A. In simple harmonic motion, the acceleration varies simple harmonically with the same frequency as that of the displacement. In SHM, the graph between acceleration and displacement is a straight line which passes through the origin and has a slope of minus omega square. Here you see some farmers are working in their field. You see some people are working in their field. They like to work, they like cultivation, and they are doing this. Jai Bajrang Bali, please help me. I want to go back to my home with a hike of 1,000, more than 1,000 times in my salary. Please help me. Bajrang Bali, Hanumanji, please help me. You are the devotee of Lord Ram. Please help me. Jai Shri Ram, Jai Sita Ram. The next point in this topic is phase relationship between displacement, velocity and acceleration in simple harmonic motion. The displacement of a particle executing simple harmonic motion is given by x equals to cap A into cos omega t plus phi, and velocity v equals to dx by dt equals to minus omega a sine omega t plus phi, because differentiation of cos is minus of sine, or v equals to omega into cap A into cos omega t plus pi by 2, and acceleration is A equals to minus dv by dt equals to minus of omega square into cap A into cos omega t plus pi, or A equals to omega square into cap A into cos omega t plus pi plus pi. Thus from above we get phase of displacement omega t plus phi and phase of velocity omega t plus pi by 2, and phase of acceleration omega t plus phi plus pi. With this we conclude that the velocity in simple harmonic motion is leading the displacement by a phase of pi by 2 radian. The acceleration in SHM is leading the displacement by a phase of pi radian, and the acceleration in simple harmonic motion is leading the velocity by phase of pi by 2 radian. With this, I like to end this lecture, and in the next lecture, the next point will be discussed. So let's tell Jai Bajrang Bali, Jai Hanumanji, Jai Shri Ram, Jai Sita Ram, Om Namah Shivaya. Please Bajrang Bali, help me to get a job in my own country.